Okay, let's look at some of our other derivatives of our existential. So basically, e to the x and natural log. So differential rules for the natural exponential functions. So we're looking at, let's change this color, the derivative with respect to x of e to the x. Okay? So this is our formal derivative notation, derivative of this function with respect to this variable. So this is going to change in the future and maybe be a t or whatever our letter is. But so the derivative of e to the x is, drum roll please, itself. The derivative of e to the x is itself times whatever the derivative of the power is. So we do, in fact, have a chain rule with our exponential equation here, e to the x. It's e to the x times the derivative of whatever your power is going to be, right? So we have a couple of examples here. Notice our powers are more than just a single variable. So the derivative of e to the x is whatever you're given times the derivative of your power. Right? That's using the chain rule. So if it was just e to the x, then it's e to the x times 1, which is e to the x. Okay? It is its own derivative, very unique. There's not many other, I don't think there's any other functions that are that way. So here we have e to the sine x. E to the sine x. So what is the derivative of e to the sine x? Well, it is itself. So e to the sine x times, what is the derivative of sine? Cosine. Okay, so I guess we could simplify this and write cosine x e to the sine x if we really wanted to, but we don't have to. You can write e to the sine x times cosine x, and that's perfectly okay. So it's the original function times the derivative of its power. Okay, so let's go to the right and see what we have over here. E to the 2x plus 3. Okay, so we write down your derivative notation. F prime is e to the 2x plus 3, right, itself. It is its own derivative times the derivative of 2x plus 3, which is 2, because that's the coefficient of x. So this one we can write, in fact, 2e to the 2x plus 3 makes more sense to write this than it did as our trig one. So let's go back to that first column. 3 times e to the 2x. Okay, so 3e to the 2x power. So f prime is equal to, right, nothing happens with the 3, it just hangs out there. 3e to the 2x times, what's the derivative of 2x? Well, that's 2. So now I have some things I can multiply together. Numbers multiply to numbers. So this will be 6e to the 2x. Okay. Oh, as an aside, what if I wanted to take the second derivative? Right? So what's the derivative of my derivative? Well, that would be exactly what I began with, 6e to the 2x times another 2, right? Because that's the derivative of 2x. So I have some more things I can multiply together to give me 12e to the 2x. Okay, and we can go ahead and take derivative after derivative after derivative, right? E will never run out of derivatives. You can always have another derivative for e. Oh, what's going on here? So now I have to use my power rule, right? So here I have a linear function multiplied by an exponential function. So we're going to have, right, this is a product rule, one, because I am multiplying two functions together. So I'm going to use the product rule. Okay, so remember your product rule says it's the first times the derivative of the second, so ab prime plus a prime b. So you're taking the derivative of one and multiplying it by the non-derivative of the other, right? Itself, and then you're switching that around with a plus. Okay, so this is the product rule. So we start with 2x plus 3, right? That is the a, the first one, by itself. And what is the derivative of e to the 3x? It's e to the 3x times 3, right? So here we have to use the chain rule in order to take the derivative of e to the 3x, which we will always do with an e problem. Plus, now we do the derivative of 2x plus 3, which is 2, right? Just 2, and multiply that by e to the 3x. Okay, so let's do some simplifying here. Remember, this is one thing, 3e to the 3x. So if I multiply that by this, right, that gives me 6x e to the 3x. And if I multiply that by this, I get 9e to the 3x. And then how many do I have here? Well, that's just 2e to the 3x's. Okay, so I'm doing some exponential simplification. So this was 3, right? So 3 times 2 is 6, and then I have my x, and then I have my e to the 3x. 3 times 3 is 9, e to the 3x. So what can I combine? The 9e to the 3 and the 2. How many is that? That's 11 e to the 3x's. Now, you might see one other thing done, and that's the fact that both of these have an e to the 3x in common. So you might see it factored out. So you should or could see this represented as 6x plus 11 times e to the 3x, right? That might be how you see it as opposed to the sum of two different things. Okay, there's a couple more here. Let's do this one, right? This is another product rule. We have your two functions. So here is your a, and here is your b that we are multiplying together. Okay, so this is once again a product rule derivative. So it goes like this. It goes the first times the derivative of the second, right, which is e to the 2x, so itself times the derivative of the power, which is 2, plus the derivative of x squared is 2x times e to the 2x. So let's do some simplification. This is 2x squared e to the 2x, and this, well, this is just 2x e to the 2x. So then if we are going to use our common factoring technique, this would become 2x squared plus 2x times e to the 2x. Okay, so almost every exponential product rule problem will have a common e value, right? Because the derivative is itself. So now that we've done some exponentials, let's flip the script and do some of the exponentials inverse, which are natural logs. So derivative of natural log. Like an exponential, these are almost always chain rule problems. So remember, natural log is ln, or log base e. So I try to always write my natural logs in cursive so that I don't differentiate between 1n and ln and absolute value n1, right? All kinds of crazy things. So natural log of x is, drum roll please, no, it's not itself. Nope, it's actually 1 over x. 1 over x, and of course times by the derivative of whatever your argument happens to be. So there's always a chain rule with natural log, unless this is just an x, right? Because the derivative of x is 1. So the derivative of natural log is 1 over the argument, so this is natural log's argument, times the derivative of the argument. In other words, x prime over x. So let's check this out and do some product, or rather quotient rules with natural log. So here we have the natural log of 2x minus 3. So we start with the notation, the derivative, so f prime is 1 over all this stuff here in parentheses, which is 2x minus 3, times, what's the derivative of 2x minus 3, which is 2. So we can, of course, simplify this to 2 over 2x minus 3. Right? That is the derivative of the natural log of 2x minus 3. So let's check out some more problems. The natural log of this quadratic. Okay, I guess if we want to practice some derivatives, that's excellent. So in the denominator, always goes your argument, right? So 3x squared plus 2x. And the numerator goes the derivative of your argument. So what's the derivative of 3x squared plus 2x? 6x plus 2. Okay, the natural log of cosine. Not that we would ever want to actually do this, but sure, natural log of cosine. This is some good math practice. On the denominator goes the argument, so cosine. And in the numerator goes the derivative of cosine, which is negative sine. Oh, I'm sure we can also apply a trig ratio here. What is sine over cosine, aka tan? So this would simplify to the negative of tan, right? Sine over cosine is tan. Let's see what else we have. The natural log of a square root. Okay, we can handle this. Natural log of a square root. So remember, your square root is your argument. The square root is the argument. So the first part is pretty okay, right? The derivative of the natural log, well, that's nice. That's just 1 over the argument. So square root of 2x minus 4. Now, the question is, how do we take the derivative of the square root of 2x minus 4? Okay, so we're going to put this as a 1 over, and then we're going to take the derivative of it over here, because it's going to take a little bit of space. All right, and if you remember anything about the square root's derivative, it is a fraction by itself. Okay, so I don't know if you remember this, but the square root derivative is 1 over 2 times the square root of x. And because of chain rule, we're going to multiply it by the derivative of your square root also. Okay, so anytime you have anything other than a plain old x underneath any type of a mathematical operation, you need to think chain rule. Okay, so we have the derivative of your argument over 2 times the square root. Exactly what it is. Okay, so this is how we take the derivative of our square root. So let's see if we can apply that formula over here. Okay, so in our numerator goes the derivative of your argument. So what's the derivative of 2x minus 4? That's a 2. So 2 is the derivative that goes up here. And in the denominator, well, I have a couple of parts. I have the 2 on the outside, and then I have to have the 2x minus 4 on the inside, right? Whatever is here remains in your problem, right? All of those things stay the same. So root 2x minus 4 times 2 over 2 root 2x minus 4. So let's see, how much algebra do we want to do in here? Well, what's 2 divided by 2? Well, that's 1. We can simplify that pretty easy. So we have, a radical times itself. What's a radical times itself? itself, right? So no more radical. Oh, look at that. That simplifies nicely to 1 over 2x plus 4. This one simplified much nicer than I thought it was going to. Okay, so there we have your natural log derivatives. Remember to use the chain rule and our exponentials. So we're going to come back and finish up with some of these ones. Okay, so this one is definitely a chain rule problem. Okay, so what is our outside most? The outside most is a square root, right? So at its heart, this is a square root derivative. It's the square root of e to the 2x minus 6. So just like we did a second ago, what is our form for the derivative of a square root? It's the derivative over 2 times the square root of your function. Right? So it's the derivative of your argument, where in this case, our argument is an exponential function. Okay, so there's multiple parts to that, but that's going to be the same as what we have down here. Okay, so we're going to take the derivative of e to the 2x minus 6 in the numerator, and we're going to leave everything alone for our denominator. So let's see what this can look like. Okay, so let's just do the over, right? Nothing changes, so 2 square root of e to the 2x minus 6. Okay, so there's that part. There's your square root derivative, right? Because that's what this is. It's the square root of something crazy. So we take the derivative of our square roots. Now let's deal with the something crazy. So what's the derivative of e to the 2x minus 6? Itself times the derivative of 2x minus 6, which is 2. Oh, guess what we can simplify? The 2 and the 2 divide to give us a 1. That's very nice. So we have e to the 2x minus 6 in the numerator and the square root of e to the 2x minus 6 in the denominator. And I am perfectly happy with leaving it just like that. Okay, so there's one more. I apologize, the bell will ring when class is over. So this is our quotient rule, low d high minus high d low. So we write our fraction, the derivative of it's low d high, so there we have. What's the derivative of e to the 5x? That's 5 e to the 5x, right? Because the 5 will eventually be in the behind, e to the 5x times 5. So low d high minus, there's the bell, e to the 5x times, what's the derivative of 3x squared? 6x. All over 3x squared squared. Okay? So let's see, what do we have when we simplify the numerator? I've got 3 times 5, which is 15, x e to the 5x, minus 6x e to the 5x over 9x to the 4th. Yes, 15x squareds. 15x squareds. So if we continue simplifying, we can pull out an e to the 5x from our numerator, and we can pull out an x. So we have 15x. Actually, we can pull out a 3, can't we? We can pull a 3 because they both have a multiplier of 3. 15 has a multiplier of 3. 6 has a multiplier of 3. So this is 5x minus 2 in the numerator, and in the denominator we have 9x to the 4th. Okay, because there's some things that we can simplify here also. We can do 3 divided by 9, right? This is reduces. We can get rid of one of these x's with one of those x's. And I believe our most simplified answer is going to be e to the 5x times 5x minus 2 divided by 3x cubed. I think that's going to be as far as we can go algebraically. Okay, so the derivative of e to the x, right, is itself times the derivative of the argument, right? This is the chain rule portion of our derivative. And the natural log is, once again, its chain rule, so we have the derivative of your natural log argument divided by that argument. Okay, so let's memorize those ones and then learn to do the algebra to simplify as much as we can. All right, have a great day. Bye-bye.